This is a summary of a paper presented at the Hyderabad Vedic Maths Conference in 2019. It's about Tirthaji's chapter 31 of his book Vedic Mathematics, which is titled Sum and Difference of Squares and is only 4 pages long, but it's a fascinating chapter. And Tirthaji says, we often have to deal with the difference of two square numbers, the addition of two square numbers, etc., etc., and it is desirable to have the assistance of rules governing this subject and benefit by them. So first he discusses about the difference of two square numbers, and he gives us this formula here for expressing a number as a difference of two square numbers. It's easy enough to prove that this is true. And to illustrate, let's suppose we want to express 12 as a difference of two squares. We first of all express 12 as a product because the AP here is a product. So if we say 12 is 12 times 1, for example, then the A can be 12 and the B can be 1. And if we put those in here, we work out half the sum of 12 and 1, which is 6.5, and half the difference, and we get 5.5, and so 12 is 6.5 minus 5.5. So that's pretty straightforward. We can also write 12 as 6 times 2, and so we take half the sum and half the difference again, and we get 4 squared minus 2 squared for 12. Or we can write 12 as 4 times 3, and the same process gives us 3.5 squared minus a half squared. So this is very nice, and it's a complete solution to the problem of expressing a number as a difference of two squares. One thing which we can do with this is to find two sides of a right-angled triangle when we're given one side only. For example, find the other two sides of a right-angled triangle given the base is 5 and all the sides are integers. So it's like this. And you'll see, of course, that 5 squared is the difference of two squares. It's this squared minus this squared. So we need to express 5 squared as the difference of two squares, 25. So first of all, we write it as a product, 25 times 1. And then we apply our formula. We get 13 squared minus 12 squared, and it's the only solution. Now moving on to the second part of Tirthaji's chapter 31, on expressing a given number as a sum of two squares, Tirthaji employs certain specific triples, and he uses them more than once. And these triples are interesting. This is the first one, 9, 40, 41, and these are others. And he gives a method, apparently, for expressing a number as the sum of two squares, and then another method, using the same triples as illustrations. Well, it's interesting, if you look at these particular triples, you can see why he might have used them. The angle in this triple is 0.057 radians. In this triple it's 0.035, and in this one it's 0.0141. And this is interesting because you see the 35 here in blue and the 35 here, and here we have 57 and 57 in green. So there's a connection between these triples. And the same here, this one is sort of self-reciprocating because you get 141 here and it also comes up in the angle. But if we multiply 35 by its angle, the first element of this triple by its angle, you get this number, close to 2. If you do the same for this one, 57 times 0.035, you also get a number close to 2. And if you multiply this first number here in this triple by its angle, you also get a number close to 2. So suppose we call the first number A. Then we could say that A times A, where A is the first entry of the triple and capital A is the angle, A times A equals 2, approximately, for small angles. And the smaller the angle, the more accurate this equation is. So a times a is approximately equal to 2, and we can use this for finding angles in triples if the angles are small. So suppose that a is 101, which actually means that the triple has a small angle. We can plug that a value into here and get the angle. It'll be 2 divided by 101, which is this number here, to 6 decimal places. And the correct answer is only differs by 1 in the 6th decimal place. So we can use this little formula to find an angle given the first side. Conversely, we can find the triple given the angle if it's a small angle. So suppose the angle is 0.06 radians, which is small. Then we can find a from here, which is 2 divided by capital A. So 2 divided by 0.06 is 33, the two significant figures. And therefore the triple will be 33, 544, 545. So we can generate triples from angles and angles from triples. Once we've got our 33, we can apply Tirthaji's method from before for the difference of two squares to come up with the other numbers. But there are other ways as well, because you may notice if you square this number, you get 1089. And if you add these up, you get 1089. So that suggests another way of getting the other numbers in the triple. You just square this number. You could add 1 and then divide by 2 to get this number, and then this is always 1 less. I will be following that up in the next slide. So, how does Tirthaji suggest finding the sum of two squares? What is Tirthaji's method for expressing a number as a sum of two squares? Well, he gives two methods, neither of which seem to actually achieve what he sets out to do, but he does give these two methods. And in the second method he writes, the square of the given number is the sum of two consecutive integers at the exact middle. For instance, if 7 be the given number, its square is 49, which can be split up into two consecutive integers, 24 and 25. Therefore, 7 squared plus 24 squared equals 25 squared. But he says 7 is the given number, which suggests that that's the number we're trying to split up into the sum of two squares. And that's not what we've done here. We've got 25 squared as the sum of two squares. However, we can get something out of this because there's a connection between 7 and 25, which can be expressed by this equation here. Once we've squared our given number, and we've got its square, in this case 49, we can add 1 and divide by 2 to get the largest number of the triple. So 49 plus 1 is 50, and half of that is 25. So 25 is 7 squared plus 1 over 2. So this is a connection between the number, the hypotenuse of the triangle, and the given number. And we can express it as an equation. If m is the hypotenuse, then it's equal to a squared plus 1 over 2. A, remember, is the first number, the 7 in this case. So that's a way of getting the hypotenuse from the first number, and we can reverse it to get a from this formula. And a is the square root of 2m minus 1. We want to do this because it's a that we want to express as the sum of two squares, not m. So take this formula, let's go on to a new page. A is the square root of 2m minus 1. And let's see how we can use it. Suppose you want to express 41 as the sum of squares. M is 41. And so we can get a from this by doubling it and subtracting 1 and taking the square root. 82 minus 1 is 81, the square root of 81 is 9. So a is 9, and 9 is 4 plus 5, the sum of two consecutive numbers, and therefore 41 is 4 squared plus 5 squared. So here we've taken a number and we've expressed it as the sum of two squares using this little formula. Here's another example. Express 85 as a sum of squares. So now m is 85, and so in our formula we double it, we get 170, subtract 1 to get 169 and take the square root, which is 13. We then express 13 as the sum of two squares like we did before up here. 13 is 6 plus 7, so therefore 85 is 6 squared plus 7 squared. Well, this is very nice, but it only applies for triples of a certain type, and a full method for expressing a number as the sum of two squares we'll be giving in a future paper. So to sum up, there are basically three things we've done here. We first looked at Tirthaji's method for expressing a number as the difference of two squares and seen that it can be used to find the other two sides of a triangle when the base or height is given. Then we saw that there's something special about the triples that Tirthaji has chosen in his examples, and they lead to this special relationship that AA is approximately equal to 2, and we can make use of that for triples with small angles to find little a or big A. In other words, to convert between angles and triples. And this does lead, in fact, to a general method of converting. It doesn't have to be for triples with small angles only. And finally, Tirthaji's text on the sum of squares can be developed to express a given number as a sum of squares for triples of a certain type.